And I'm going to talk to you about, what's happening in AI. I don't know if you've noticed, but it's a thing these days. And we have many people at Google working on this area. So I'm presenting the work of not just my work, but many, many people at Google and elsewhere. So a few observations, which may not come as a huge surprise to you. So machine learning and AI have really changed our expectations of what is possible with computers. If you think back 10, 15 years ago, computers couldn't see very well. They couldn't really understand speech all that well. They definitely couldn't understand language very well. And now we have tools that enable computers to interact with people in a much more natural style because they understand the modalities that people understand and want to communicate with. And along the way, increasing scale of larger amounts of compute, larger amounts of data, and more larger scale models have delivered better results. Nearly continuously for the last sort of 13 or 14 years, this has been the trend and seems to be holding up even today. In addition to scale, algorithmic and sort of model architecture improvements have also provided massive improvements as well. And these two things multiply together, right? If you can have much larger scale and much better model architectures that are able to learn more, per floating point operation, those things together mean instead of, 20x from scale, you have 20x from scale and 50x from algorithms, and you end up with a 1000x better thing than you had not that long ago. Also, the kinds of computations we want to run and the hardware in which we want to run them are changing dramatically. So 4 observations, which are maybe not surprising. First, neural nets and gradient descent. These seem to be key building blocks for how do you actually build truly intelligent computer systems. And they're not new ideas. They're things that have been around for a long time. They were invented in the 70s and 80s. And there was actually a lot of excitement about them in the late 80s and early 90s. I first ran across them in a intro lecture where I was introduced to neural networks roughly like this. We have this kind of nice, very abstracted away version of how we think real life neurons behave, where you have a bunch of inputs, you do some processing, and you decide, are you going to fire or not? And what strength are you going to fire? And you have connections of these things. And then backpropagation is a really nice algorithm that enables you to adjust the weights on the edges of all these connections in order to make the model behave more in the way that you want it to behave, where you give it a bunch of examples, and backpropagation enables you to make the model learn the behavior you want. So I saw these as an undergrad in 1990, and I got super excited. And I said, oh, wow, that seems like a really good abstraction. It feels like it's a trainable thing, and it can learn almost anything. And at that time, we were not using very large neural networks because we had really pathetically wimpy computers. But I said, oh, maybe if we use the parallel computer in the department, we could train much bigger neural networks, and that would be great. Maybe we just need to use 32 computers instead of 1. And then we could train really impressive neural nets. That would be nice. So I asked the professor who introduced the neural networks topic in one of the classes I was taking if I could do a senior thesis with him, Vipin Kumar. And he said, sure. So I played around with 2 different approaches for training neural networks in parallel. One is, this is what you would now call model parallel and data parallel training. But I called them pattern partitioned and pipelined approach. These speed up curves are interesting, but they taper off because I did the stupid thing. I didn't make the model bigger and bigger as I increased the number of processors. I just made it, much harder to parallelize with a fixed size model. But I sort of filed that away as like, oh, that's an interesting abstraction, and it seems like something I should pay attention to. But then I ignored it for, the next 25 years. Okay, so now I'm going to give you a whirlwind tour of a bunch of advances in the field of ML that have happened in the last 15 years that are really all, combined together to produce today's, most sophisticated models. How did today's models come to be? Well, it was through advancements like the ones I'm going to describe. So the origin of my getting back to working on neural nets at Google was I bumped into Andrew Ng, who's a Stanford faculty member, and in one of our micro kitchens, and I said, oh, what are you doing here? He's like, oh, I'm not sure yet, because I just started a week ago. But my students at Stanford are doing interesting things with training neural networks for speech and vision. I'm like, oh, that's cool. we should train really big neural networks, I said. And so that was the origin, because we actually had quite a lot of computers in those days. And I said, oh, why don't we try training very, very large neural networks? And so we built a software system that enabled us to express neural network and connectivity of those neural networks and do both model and data parallel training across many, many computers. And that enabled us to train neural networks that were 50 to 100 times larger than what the largest ones we could find anyone talking about. We had a way of doing this where we had actually many, many asynchronous replicas of the model, getting updates of what the current parameters of the model were, churning away on their local batch of examples, computing a gradient, and sending it to this distributed set of parameter servers in order to update the parameters of the model. This is, because it's asynchronous, definitely not the right mathematical thing, because in the meantime, the model parameters have moved from the other replicas giving them the parameter servers updates to the parameter model, to the parameters. But it seemed to work, so we were sort of happy anyway, despite it being sort of theoretically wrong. And one of the first things we trained was a very large model to do completely unsupervised learning on 10 million random YouTube frames. And interestingly, we had a kind of a locally connected neural network for computer vision that would use a reconstruction loss. So it would try to take a high-level representation of the neurons at the highest level of the model and then try to reconstruct the pixels that have been given as input. And because that bottleneck layer forced the model to sort of learn higher level abstractions than the actual raw pixels, what we ended up finding was at the top level of this model, some of the neurons had learned to be sensitive to whether or not there was a face of a cat in the image. Some of them learned to be sensitive to whether there was a face. Some were sensitive to is this the outline of a person? All without being told any of these images contained any of those kinds of objects. So it's kind of neat to see that you could learn these high-level abstractions and representations from a purely unsupervised objective. What we could then do is use the initialization of this unsupervised training in order to train with a supervised method to try to do computer vision image classification. And unfortunately, we used the 22,000 category version of ImageNet, which is a more thinly traded version than the 1,000 category one that most people are most familiar with. But we got a 70% relative improvement in ImageNet 22K state of the art by initializing with our unsupervised model and then doing supervised learning on the training set for that data set, which is quite a large relative improvement. So we were happy with that, and we saw that scale really mattered. We also started to do a bunch of work in using neural networks for language tasks. And one of the things we found was that even relatively simple models where you have a vector-based representation of words or phrases, so that you have a nice 1,000 or 500 dimensional representation of each word or token, and have relatively shallow models. So in fact, we had just the embedding vector, and then we would use the embedding vector of the word to try to predict nearby words. That was one of the approaches we tried. And what we found was that if you apply this to lots of text and use this training objective, you end up with nearby words in the high dimensional space tend to be related ones. So like cat and puma and tiger are all low distance in the high dimensional space, and also the directions are meaningful. So you go in the same direction to change the gender of a word in a gendered language, regardless of what word you start with, king and queen versus man and woman. A year or two later, three of my colleagues, Ilya Sutskever, Oriol Vignald, and Kwok Le, used a neural encoder using an LSTM to essentially be able to learn an encoder for one sequence and then a decoder for a different sequence. And when you initialize the state of the LSTM by running the encoder, that ends up sort of capturing the things that have occurred in that input sequence and enables the model to then use that initial state to then do a good job of predicting the target sequence. So the canonical example use case of this is language translation, where maybe you have a bunch of English-French sentences, pairs that mean the same thing, and the input sentence is English. And so when you're training, you try to decode the French sentence, and you get a supervised learning objective for every token or for every word. And then when you're trying to translate a new sentence, you just use the encoder to encode the LSTM state and then decode from that state in order to produce the translated French sentence. So as we saw more and more success of neural networks, and in particular scaling up neural networks for problems in computer vision, speech recognition, and language, we were starting to both get excited but also a bit worried about how we would actually deploy these much better models. So this is kind of the origin of how we started to create our own tensor processing unit chip program. Is I did this back of the envelope calculation and said, okay, we have this really nice high quality speech recognition model. It halves the error rate for speech recognition, which is a huge improvement. It's sort of equivalent to 20 years of speech research in like 6 months since we started the project by training just a very large, not particularly sophisticated model architecture. It's like a 8-layer fully connected neural net, just trained on a lot of data. And that back of the envelope calculation said if we wanted to deploy this to a scenario where we had 1 billion users talking to this model 3 minutes a day, we would need to double the number of computers Google had. And that didn't seem very tenable for rolling out a better speech recognition system. So that really convinced us that exploring much more specialized computational devices for doing neural network inference and later neural network training was going to be a fruitful path. And so this sort of bootstrap got us to really approach that with conviction and started up a chip design team in order to build these chips. And then the first chip emerged 2 years later, as hardware projects tend to do. They take a little while, but we eventually produced the TPU V1 chip, which took advantage of 2 really nice properties of neural networks. The first is that reduced precision is fine, especially for inference. So you're perfectly happy with about 7 or 8 bits of precision, not 16 or 32 or 64, as most people are thinking about in terms of floating point computation things. And also that nearly all of the models we were exploring were made up of different combinations of a handful of specific kinds of linear algebra operations. Things like matrix multiplies are at the heart of them, and then certain kinds of dot products and normalization and scaling. But if you think about most of the machine learning algorithms of today, different rearrangements of those kinds of operations mean that you can build an accelerator that is capable of very high performance, reduced precision linear algebra, and that can be applicable to a pretty wide range of neural networks. And it's much more efficient because that's all it needs to do. It doesn't need to do anything else. It doesn't need to run Microsoft Word or Chrome or anything else. And so TPU V1 turned out to be 15 to 30x faster than contemporary CPUs and GPUs, and 30 to 80 times more energy efficient than contemporary CPUs and GPUs. And it's also now the most cited paper in its 50-year history. So we then turned the chip design team's attention to the training problem because we felt like being able to scale up training more than we were able to on CPUs and GPUs was going to be important. And so this is where the focus has been for quite a while. And we've now produced many, many generations of TPUs that are essentially machine learning supercomputers, right? It's more than just a single chip, unlike TPU V1. Instead, it's lots and lots of chips connected with a custom high-speed interconnect that enables us to distribute model training over those chips and communicate both activations and parameter updates and gradient updates across that custom interconnect. Version 4 introduced this funky thing where we have an optical interconnect for racks of these accelerators. So there's a rack of 64 accelerators, and we can make it seem as though that rack of 64 accelerators is right next to another rack of 64 accelerators, even though they're 100 meters across the data center floor. And if that rack fails, we can swap in another rack and make it seem as though this rack is now right next to that one in terms of the net topology, which is important as you get more and more scale, you end up with failures, and so you want to be able to reconfigure things like that. And so we've seen, continual hardware performance scaling. So if you look at TPU v4 here on the left column, the peak flops per chip is about 275 teraflops. The max pod size was 4,096 chips, and now we're sort of at roughly double that pod size and a much more HBM memory and much more memory bandwidth and many more flops per chip. If you compare the peak performance per pod, which is sort of the largest network configuration we have of the custom interconnect, the TPU v2 pod is 1x, and the most recent sort of v6, now we've stopped numbering them, sadly. It's hard to keep track of. But Ironwood is the 6th generation of TPUs, is about 3,600 times the performance per pod of TPU v2, and it's also much more energy efficient, so about 30x better energy, flops per watt, which is what you ultimately care about in terms of energy cost. The other thing that has happened in the last 15 years is open source tools have really enabled the whole community to build using the same pieces of abstraction and software libraries, and the community can work on sort of improving those tools as well. So we developed a series, a software called TensorFlow, that based on our initial lessons from the sort of 2011 to 2014 era, with an internal software library that we were using to parallelize computations across many computers and train large models and do inference. And then more recently, various people at Meta and elsewhere introduced PyTorch, and then another group of people at Google have introduced a more functional style paradigm computation called JAX. All of these are great systems, and we have been using JAX for our Gemini training, and it's been great. And then in 2017, a number of my colleagues worked on coming up with a better architecture than the sort of recurrent LSTMs that were kind of the state-of-the-art models for language at the time. And the observation they had was really, in an LSTM, you have a vector of state of sort of the current representation of the state, and then when you advance one word one token at a time, you update that state. And there's a sophisticated thing that sort of updates the state, and then you go on to the next word and you update the state again. And so as you progress through, say, 100 words of a sentence, you update the state 100 times. And there's two problems with that. One is you have this sequential process. Every word, you have to wait for the update of the state, and there's a sequential dependency on that state being ready before you can go on to update the state for the next word. So it's not very parallelizable, which is not good on modern hardware. And the other thing is you're trying to force all the things you went through into a single vector that you have all the things you might want to remember from the things you went through in a single vector, rather than just saving all the vectors you went through and then being able to look at them as you wish later in the sort of language modeling process. So the key observation in the transformer model is let's save all those vectors or some representation of those vectors, and then pay attention to them in a way where we have a learnable attention mechanism. And what they were able to show was that compared to LSTMs of 1, 2, or 4 layers in red there, the test loss on the y-axis went down considerably using a transformer, and no matter what model scale you looked at. So sort of a 10 to 100x less compute and 10 times smaller model gave you, with a transformer, would give you roughly the same quality as you would get with an LSTM that's much larger and much more compute intensive. In 2018, I think people really started to take seriously the idea, well, I guess in the Word2Vec work, we were already sort of doing that. But in 2018, really looking at how could you do language modeling at scale with self-supervised data. And just the observation, there's a lot of text in the world. And so self-supervised learning on this text can give you almost unlimited amounts of training data where you know the right answer, right? Like you have text, and then you hide the next word, and you try to guess the next word. And if you guess it correctly, that gives you get a sort of a 1. And if you guess it wrong, that gives you a clear error signal that you can propagate into improving the model so that in such settings you will guess better next time. And so this is really one of the major reasons that these chat and language models have gotten, yeah, I created a custom example for this week. And so there are two kinds of training objectives that people typically use. One is called autoregressive, where you get to look at the prefix, everything to the left, and try to predict the next word. So Princeton blank, that word is a little bit hard to predict. Could be Princeton, New Jersey. Could be Princeton University. Princeton University blank. That one's hard to predict as well. Is cold in the blank. That maybe is a little easier to predict. So that's autoregressive. And then fill in the blank is where you get to have a training objective where you just hide. You get to look in both directions, and you hide some of the words. And you try to force the model to guess the missing words that you've hidden. And again, you get this nice, sophisticated, very, very crisp error signal that you can use to train the model. And you can just train on lots and lots of text, either of these objectives. The fill in the blank one tends to be used to build representations that give you a good representation of a bunch of text, but you can't really use it for a chatbot because you don't have the things to the right. So you have to sort of end up using mostly autoregressive models for conversational applications, but fill in the blank also has some good uses. In 2021, a number of other of my colleagues applied transformers to computer vision. At that time, the sort of state of the art was to use various kinds of convolutional models, which have these kind of local receptive fields, and then you build up and share the parameters among different positions in that in the image. And instead, you can just apply a transformer-based model to the same problem. And what they found was, again, you get a much better, if you look at the TPU core days to reach certain levels of accuracy, the TPU core days are much lower and the accuracy is higher compared with, say, ResNet 152, which was kind of a good state-of-the-art model at that time. And the other nice thing is you can kind of see what the attention mechanism is paying attention to. So it gives you a little bit of model interpretation of like what is it paying attention to in order to make say a classification prediction that middle one is an airplane. Another area that we have done a bunch of work in, including myself, is in sparse models. In a dense model, you have a bunch of parameters in the model, and every inference or every token, you activate the entire model in order to make the prediction for that example. And that seems kind of, that's not how our brains work, right? We have very different pieces of our brains that are useful for different kinds of things. And we activate the right part. So while I'm, worried about the garbage truck backing up at my car, some parts of my brain are active, and the part that thinks about Shakespearean poetry is not active. So with sparse models, the idea is we want to have different pieces of the model that are good at different kinds of things. And then be able to automatically learn not just those experts, but also learn the routing mechanism to learn which pieces of the model to actually activate for those different examples. And so it gives the model much larger capacity, but still keeps the inference cost relatively low because you're only activating a small number of the parameters in the model. And importantly, it gives you an 8x reduction in training compute for the same accuracy. That's choice A there. Or you could choose to spend the same amount on training the model and get a much better model, right? Same amount of compute. That would be choice B there. And often these kinds of things, you choose a bit of A and B and end up kind of somewhere there. But this has been a really important tool for making our model better and better over time, is having sparsity be a part of the mix. There's a whole litany of work that both I and my colleagues have done in this general area, looking at various aspects of how to do the routing, how many experts do you activate, and so on. Another thing we've been working on is building up abstractions for distributed ML computations. So Pathways is a system we started working on quite a while ago that really wants to abstract away this pile of accelerators underneath your computation and give you, the sort of researcher, the illusion that you just have a giant computer with tens of thousands of chips attached to it, and you can mostly just focus on the machine learning computations you're trying to express. And underneath the covers, Pathways does a bunch of work to manage how to communicate the machine learning computation you've expressed amongst all these chips. And so it will, for example, use within one of these pods it will use the custom TPU interconnect. When you go across the pod boundary in the same data center building, it will use the data center network. When you go across buildings in the same data center campus, it will use the purple network link. And when you go across, perhaps widely distributed metro regions, it will use the sort of wide area network links. And then when you actually put JAX on top of pathways, what that means is that we can drive the entire training process from a single Python process on one host. So that Python process says, oh, great, I have access to these many thousands of TPU chips, and I can run this computation. And pathways kind of deals with what happens when different pieces of the system fail, and swapping in new parts, new hardware under the covers. Another thing that tends to happen when you run at increasingly large scale is, sadly, not all chips or machines or network cards or cables work as designed. That's a very sad but true state of the world. And in particular, some of them don't just fail in ways that you can just detect them immediately and replace them. They sometimes non-deterministically sort of produce incorrect results silently. And sometimes that's related to dynamic conditions like the temperature of the rack at that particular moment. This is really challenging when you're running independent compute on these things, but it's really worse when you're trying to have all these chips perform as a single orchestrated machine learning training computation where everything is synchronous. And this can quickly spread bad results. So like if one of these things flips one of the bits in the exponent field of your gradient, all of a sudden you'll get 10 to the 20th propagating as a gradient instead of 0.2. And that makes you very, very sad. And so we monitor during the training process all kinds of metrics about the health of our model. And in particular, you can look at, for example, the norm of the gradient at every layer of the model and see, are you seeing spikes in that? So here's an example of a spike due to one of these silent data corruption things. Now, not all spikes are necessarily due to these kinds of machine issues. Here's another spike. There is no SDC. This is just some particular batch of examples that contain something that caused a very large gradient to occur. And it's a little hard to discern those things. So one of the ways we do this is we have deterministic replay that we trigger automatically. So if we see a gradient spike, then we will effectively replay that step or the last few steps and see if we get the same answer. And if we get the same answer, we conclude, well, that's probably okay. That was probably due to the data, not due to hardware errors. But if the hardware errors are causing the issue, then hopefully we get a different answer the next time we replay it. And you can also have cases where we don't get a gradient spike, but there is actually silent data corruption happening, but it doesn't cause a very large spike in the gradient. And so that is sort of benign to the model, even though we didn't detect it. So all kinds of things can happen. It's very fun. The pathway system is part of the way in which we transparently handle these things. So for example, let's say these blue pods or slices of pods are currently part of our synchronous training jobs. We have these 7 blue things. We have a hot spare in gray, and then we have another hot spare, and we're running a SDC checker. So we have a continuous thing that we're running even on the idle chips in order to try to weed out bad hardware before we're actually starting to use it. The defective machine causes one of these silent data corruptions. The SDC checker identifies this because we replayed and detected that there was a mismatch in the answers when we ran them twice, and we can pinpoint which pod it is and which chips. We can evict that thing and then use the hot spare to now replace it transparently in the training process and continue on our merry way. Send that thing to our repairs team, and hopefully they can figure out in more detail what's going on with it. Okay, in 2022, thinking longer at inference time became more of a thing. And in particular, the observation was that if you prompt the model to show more of its work on an example problem, and then ask it to solve a similar kind of problem, if you just ask the answer, please give me the model, just give me the answer, In this example, you prompted the model with one example problem, and you said the answer is 9, and then you gave it the problem you really care about, and the model will sort of model that behavior and say the answer is 50, and it actually gets this problem wrong. But if you give the model a worked out example, then the model will tend to work out in the similar way the individual steps to get through the actual problem solving process and be more likely to give you the correct answer, right? Which is kind of nice. This is what your 4th grade math teacher told you, and it's nice to see that ML models behave the same way. One way to view this is you're actually giving the model more compute to think at inference time, right? Because every token it needs to generate is a pass through the model. And so you can think of the length of the answer as some proportional aspect of how much compute it devoted to producing the answer. And what you see is that as the model gets to a certain scale, when you allow it to do chain of thought, you encourage it with chain of thought prompting, you get pretty large increases in the solving rate of GSM8K. Remember, this is like 8th grade math problems like the ones here. John has 5 rabbits. He gets 2 more. Maybe that's not 8th grade. That should be more like 5th grade or 2nd grade. But anyway, these are pretty simple problems. But we were very excited in 2022 about high rates of accuracy improvements on those kinds of problems. So remember that. Another thing we worked on was distillation, where you can effectively use a powerful teacher model to make a smaller and cheaper student model from the the more sophisticated predictions that the larger model can make. And in particular, like if you're doing language modeling, perform the concerto for blank, right? So the true answer in this case was violin, and that's what your training methodology would use as the signal to give you a supervised learning signal. But if you have a really good model already, what that teacher model can give you is a probability distribution over the likely next words. So it could be violin, could be piano, could be trumpet. It's almost certainly not airplane, right? Unless there's new concertos I don't know about. And so that gives a really rich gradient signal at the very top of the model that gives it much more information than just did you get violin or not, which is what the sort of non-distilled loss would give you. And so this enables you to get a lot of the capability of a very large model into a much smaller model, and also to do so with much less data, perhaps. So in the initial experiments in the paper, we were looking at a speech recognition problem. And so we had a baseline where we used 100% of the training set and got a training frame accuracy of 63.4% and a test frame accuracy of 58.9%. But if you drop the baseline to use just 3% of the training data, then you overfit on that. So you have 67% training frame accuracy, but your test frame accuracy plummets to 44.5%. But if you use the soft targets with distillation, you get quite a nice training frame accuracy, actually even better than the baseline on the 100% of the training data with just 3% of the training data. And your test frame accuracy is nearly as good as the full model trained on 100% of the data. So this is a really key technique for effectively enabling you to morph any shape model into another shape model, often a larger model into a smaller model. This is, for example, what we use in Gemini to go from the pro scale model into a flash scale model that is almost as good as the pro scale model. And then in the last 4 or 5 years, I would say, reinforcement learning has become much more important in eliciting the desired properties that these models have. And so given a pre-trained model where you've just exposed it to a whole bunch of training data of text, that model has a bunch of capabilities in it, but you want to help steer the capabilities of these models a bit. So in particular, you want to maybe encourage behaviors that you want in the way in which the model responds. You might like a certain style of response. You might like to prefer certain length responses for certain kinds of things. You might want safety properties to be put into the model, so don't engage in these kinds of topics, or say something like this in these scenarios. And you also want to enhance the capabilities by showing the model how to tackle more complex problems. And so one of the key questions when you use reinforcement learning is, where does the reward signal come from? But these do dramatically improve the model capability in a lot of domains. And the reward signals, turns out, can come from lots of different places. So one is you can use human feedback. do you like A or B as an answer for this kind of question? And have humans evaluate that and give a reward, and then have the model, or is this a good answer for this question? They can say yes or no. Those kinds of things can be very effective at making the model's behavior change pretty dramatically with even relatively few examples. You can also use reinforcement learning from machine feedback, where you have machine feedback from a different model, so often called a reward model. You can prompt the reward model saying, please say whether you prefer response A or B for question Q. And then you generate 2 responses from your base model, and then you ask the reward model which one do you like better, and that gives you a reward signal. You can also do RL in verifiable domains like math or coding, and you can, for example, generate proofs or solutions to be checked with a theorem prover and give a positive reward when the model produces a correct proof for the problem you're trying to solve. You can generate code for coding things, where you now have a reward for does the code even compile? Does the code compile and pass the unit test? You get more reward. These kinds of things. So these really help a lot in both math and coding, but also in kind of adjacent areas like more sophisticated reasoning and planning in adjacent domains. I think there's a nice open research question of how do you improve the effectiveness of RL in non-verifiable domains, and where do you get interesting reward signals from? Those are things that I think are pretty open and ripe for lots of cool approaches. In 2023, a few of my colleagues came up with this really nice method for making inference faster. One of the problems with the autoregressive decoding is, in order to have the attention mechanism have the state it needs when you're pre-filling. So if you have an input of 1,000 tokens, that you can do completely in parallel. But now if you're going to try to start generating a response, you generate the first token, and then when you finish generating the first token, you can now look at that token and be able to now generate the next token, because you need the attention state for that previous token in order to actually generate the next token. So it's a sequential process, a little bit like the problem we had with LSTMs, where you have this sequential decoding phase. And so speculative decoding is a nice approach, and you change only the decoding algorithm. You don't have to retrain your model. You have no architecture changes, no retraining, and you're guaranteed to have the identical output distribution. Okay, so the observation is decoding from very large transformer models is memory bound. So the hardware can do way more floating point operations than it can do transfer all the weights of your model into the multiplier unit in order to do the single token of decoding you want to be able to do. Observation 2 is that some tokens are a lot easier to predict than others. So can you tell me what the square root of 7? Sure, the square root of 7 is blank, right? That last token is really, really hard for the model to predict. But a lot of the other ones are very easy for the model to predict. Like after the question mark, it can probably make a prediction of 4 or 5 tokens and get some of them correct, in particular some prefix of them correct. And so the idea is you have a fast drafter model where you don't need the full sophistication of a much larger model, and you can quickly generate the next, say, 8 tokens, and then have the target large model check them in parallel. This effectively gives you a batch size now of, instead of 1, a batch size of 8. And if you accept on average 4.5 of those 8 tokens, then you've made your compute efficiency much better. So here's an animation of how this works. If you just try decoding with a large slow model at the top, you're decoding 1 token at a time. And instead, if you have a small model at the bottom that's drafting sequences of 4 tokens at a time, and then the larger model, I'm going to run that again. Okay, so now watch the bottom thing. The drafter is generating the yellow things, and then the upper model is accepting the prefix of them that is correct according to what it wanted to generate based on its own probability distribution. So this actually helps quite a lot in improving the efficiency of inference in these models. Okay, so a whole bunch of things have come together in order to actually make these modern models work well. Lots of innovations in the inference algorithms, in the training algorithms, model architecture, software abstractions, and in the hardware. Okay, so now we get to Gemini. So we actually, the sort of origin of Gemini was we actually had multiple separate groups at Google looking at language models, looking at sort of creating multimodal models of various kinds. And I sort of said, this is stupid. Why don't we all work together and have, instead of fragmenting our compute and our ideas, let's all work together and build a single kind of model that is multimodal, that has a lot of compute investment behind a more singular effort. And that's the sort of origin of the Gemini project. And so we started this in February 2023 with a bunch of collaborators from Google DeepMind, Google Research, and the rest of Google. And our goal is really train the world's best multimodal models and use them in all the places we can. And so we've produced in that time a number of different sort of iterations of Gemini generations, 1, 1.5, 2, 2.5, and most recently 3. And one of the things we wanted was for the model to be multimodal from the start. In particular, we think it's really important that it deal with language, with audio, with images, and with video, as well as other non-human modalities. Like in more recent Gemini versions, we've been including some small amounts of, say, LiDAR data or robotic control data, because you want to at least expose the model to the idea that these kinds of data exist. And then initially in the early Gemini versions, we had an image decoder and a text decoder. More recently, we've added audio decoders and video decoders so that we have a single unified model that can reason over input sequences that are mixes of any of these modalities. So you can give it like an image and some text that describes the image or what you want the model to pay attention to, and maybe a video and some audio. And you can also produce any of those things as output in an interleaved way if you want. And as I said, we're basically building on lots of these different advances. So we use TPUs, we use model parallel and data parallel training and cross data center training. We have fast and automated detection of STC errors. We use pathways, we use JAX, we use distributed representation of words similar to word2vec or the sequence-to-sequence work. We use transformers. Our models are sparse typically. We distill from larger models into smaller models. We use chain of thought decoding and more sophisticated versions of that. Speculative decoding is really important. We use SFT and various kinds of RL and a bunch of other things I didn't have time to talk about. One of the things we've been working on for a while is making our context length large, because we think the information in the context window for the model is really useful. Unlike tokens in the training data, where you've sort of taken trillions of tokens of training data and stirred them together into hundreds of billions of parameters, but it's all a little bit muddled and fuzzy. The information in the context window of the model, the input that you give it, is very crisp because you haven't mixed it with anything else. It's sort of like, I see these 900 pages of text you gave me, and I can like look at different parts of it and summarize and combine and pull out little pieces of it when I'm decoding. And so extending the context window to very large lengths has been something we've been working on, and we think is important. One of the things we've tried to keep up with in every release of Gemini since the earliest ones is that we have different scales of model. We have a pro scale model, which is the highest quality model. And then we have a flash scale model that is ideally as close to that pro scale model as we can get it. And in particular, we also want that flash scale model to be better than the previous generation's pro model, right? And so we've been able to keep that up for 4 generations now, which we're pretty happy with, because it means that the highest end thing that is perhaps slower and more expensive for a lot of use cases suddenly becomes more affordable 6 months from now, because it now has that capability in the flash scale model. Gemini 2.5 Pro we released in March, I guess, with quite good results. We've also been working on mathematical problem solving, and in July of last year, we competed in the International Mathematical Olympiad, the IMO, and we got 5 out of 6 problems correct, which is a gold medal score. We were quite happy with that. And we did it. We competed the previous year with a more sophisticated kind of jury-rigged, mathematically specialized model that used lean and theorem provers and various things like that. For this year, we used just an out-of-the-box Gemini Pro scale model with a high inference thinking time budget in order to tackle these problems. So we were pretty happy that we didn't have the sort of and we also had, in the previous year, we had a different model for geometry problems and things like that. So we were happy to have a single general purpose model that is the same one we offered to users, was able to solve and get a gold medal at the IMO. Just to give you a sense of how far we've come in mathematics. Remember back to Fred had 5 rabbits and then he got 2 more. Okay, so this is one of the IMO problems. And you can see all the 5 correct solutions of the problems we did there. But this is one of the problems. And so this is the output of our model. And you can see this is sort of fairly sophisticated mathematical style writing and formatting of proofs and so on. And we established an upper bound. We had another lemma. We constructed and made a lower bound. And then we proved that f of n is less than or equal to 4n for all Bonzo functions, which was part of the introduction of the problem. So like this is now quite a bit beyond GSM 8K, I would say. I mean, it's not research level mathematics yet, but you can see the slope is quite large in 2 years. And then our Gemini 3 model release happened in November of this year, where we were pretty happy with a lot of the benchmark results. But also we have some, we were happy with where it landed. In one of the ways that you evaluate these models in the wild is you can use this setup called LM Arena, where people see responses from 2 anonymized models, and then they say which one is better. And from lots of pairwise for their particular prompt, right? Like people can go say, can you please help me solve this mathematical problem? Or can you help me produce a recipe for my, French onion soup or something? And then people grade A or B, which is better, like going to the ophthalmologist. And through a lot of those evaluations, you can get a sense of the relative strength of different models. And that's where you get an ELO score, a little bit like a chess ranking. So one of the things we've been working on is search and AI mode. We actually want these models to be able to produce the UI that the user will see. I'm not sure this is going to work. Am I on the Wi-Fi? I might not be on the Wi-Fi. Ooh, is that going to make me sad? All right, let's enable the hotspot. That's probably easier than logging into the Princeton guest network, isn't it? One moment. Sorry. Okay. Now we're going to wait for that. Come on. Oh, there we go. Okay, great. Awesome. Now we're going to try it. Show. Go there. Go there. Haha, yay. Thank you, T-Mobile. Okay. All right, so this is basically, they put in a sort of researchy, textbooky thing about some biological thing, and now they said, show me how this works. And what it's done is created an interactive visualization of the material there, and you can use sliders to control the visualization and get a sense of the topics you're trying to learn about, which is pretty nice. You can see how this would be really useful for educational things. Here's another example. What this couple has is a bunch of recipes in English and Korean in handwritten pieces of their. So I will actually, since we have closed captions, I will speed this up to 1.25. And so they basically are taking things like that. They're asking Gemini to take all those recipes and say translate and transcribe them in English and Korean. And then it is, any Korean speakers can maybe validate. English translate. Okay, so now they're going to say, please create me a bilingual website using these recipes. Okay, so there we go. And then we added some automatically generated images. And this is a website that was created from that. So, I mean, I think one of the things about this is that this kind of sophisticated model will enable a lot of people who maybe don't have the skills to write software to get things that they want in software form. So I think we're going to have a lot more software in the world than we have now. It's kind of a cute example, but I think it's good to pay attention to what these models can do and the sophistication level of the coding and problem solving they can do. I mean, I'll skip that. Generative models for images and for video have also been improving quite rapidly, I would say. So we had an initial release of something called Nano Banana, and then we made a much more computationally expensive but higher quality version called Nano Banana Pro. And so as examples of things, you can start with that blueprint and say, please make a realistic 3D image from the blueprint. You can see how this would be quite useful for visualizing different architectural things. You can say, please annotate the original transformer architectural diagram with the important things that happen in different parts of the diagram. You can see if you're reading a research paper, getting a visualization of that could be pretty useful. You can actually view thinking in pixel space. So here, the input image is this sort of ball and ramp problem. And tell me which bucket the ball lands in. Use images to solve it step by step. Right? So you can now actually see the model will generate a series of images of its reasoning. So it goes from there, step 1, the ball rolls there, step 2, the ball rolls onto 3, and then step 3, the ball rolls onto 5, and then step 4, it ends up in bucket B. And so you can sort of see how your own problem solving probably makes these mental images of what's going to happen, and the model is able to do that and actually render that. This is like an example. You can annotate Orville Wright's airplane with different stats. 605 pounds. That's interesting. I didn't realize it was quite so heavy. I tweeted this out as an example of what it can do when we initially launched Nano Banana Pro, and a bunch of people got very sad. So no Pluto, where Pluto? So I said, okay. I too am a child of the 9-planet era. Make this image 21:9 to add Pluto and add a humorous comment. So it decided to add the, quote, former planet got demoted to dwarf planet status, still grumpy about it. And he said, perfect, we are so back. Okay, I want to touch a little bit on how we organize a big effort like Gemini. And in particular, this is a large effort. I'm now a co-author on a paper with more than 1,000 authors. Our reports are long. Even just listing the authors takes quite a lot of pages. We always try to spell something funny in the first few words of the author names. So when you have that many people trying to work together on something, you need a little bit of structure. So we have overall leads, we have program management and product management that help kind of assess, help us be organized, but also help us figure out from a product standpoint, what do we want our next generation models to do? And then we have a bunch of different sub areas that are really, really critical to making Gemini work well. So one is, model development. So in terms of both pre-training and post-training and RL, things like that. We have a version of Gemini that runs on device on our Pixel phones. So that has somewhat different characteristics and somewhat different aspects of training data and capabilities needed. In terms of capabilities, we have a bunch of areas like safety and vision, audio, code, agents, internationalization that we care a lot about. And then core areas like what data should we train on? How can we get the highest quality data we can for the token budget we have for training our next model of evals? How do we know if we're doing a good job across lots of different capabilities? Infrastructure, which is like how do we make the training process work well? How do we make the serving infrastructure work well? The code base, and then longer term research that is meant to feed in good ideas for Gemini N+2 or Gemini N+3 that will intersect the sort of at the right time. And we have people spread out all over the world. So we have about 1/3 of the people in the Bay Area, 1/3 in London, and 1/3 in many other places. So New York City, Paris, Boston, Zurich, Bangalore. Time zones are super annoying. Not much we can do about it, but the golden hours between California, West Coast, and London, Europe there's about 3 hours a day that are not too terrible for anyone. And so that's kind of nice, but that does mean you have to have asynchronous ways of working that work well. And so there are lots and lots of large and small discussion groups, chat rooms, Google chat spaces. So I'm in 200 of these. We have a request for comment, kind of internal document or tech report-y like thing, which is a semi-formal way of getting feedback. knowing what other people are working on, jotting down an idea. They range in sophistication from early stage idea I'm thinking about, I want comments on, to I've done an exhaustive exploration of 10 different variants of this idea. Which one should we put in the next version of Gemini? They're numbered sequentially, and I just looked. We now have more than 5,000 of these. So there's quite a lot of internal requests for comments that are ranging in complexity from a single page thing to something that would be a tech reporter paper. And then leaderboards and common baselines enable us to make data-driven decisions about how do we improve the model. So we have lots of rounds of experimentation. You do many, many more experiments at small scale and only progress things that seem promising to medium and large scale. Every so often we incorporate, say, successful experiments demonstrated at larger scale into a new candidate baseline, and then we repeat. And that seems to have worked pretty well. Few forward-looking thoughts. I mean, I think one area that's going to be really important is how do humans and AI agents collaborate to get stuff done, right? Like currently, a lot of the uses of these models are you have a single person sitting down with an interactive, chatbot interface doing stuff. But in the future, it seems like more work is going to happen where the human coordinating the activities of a dozen or 100 AI agents doing stuff on their behalf, where the human is probably weakly specified what it is they want. How does how can we give the right HCI paradigm for managing a team of 50 of these virtual assistants? How can the agents themselves cooperate to accomplish things? What will this enable? I think these are all pretty interesting directions. I think the million tokens of context is quite useful, and that gives you 1,000 pages of text or hours of video or whatever. But it seems like it'd be even more useful to be able to attend to a trillion tokens of stuff rather than a million. And so I think hybrid systems with learned retrieval algorithms over large corpora, and then maybe lightweight models that can be used to assess how relevant are these 30,000 documents I retrieved to the thing I'm trying to do, and then put the maybe 100 things you actually think are really, really important into the context window, and maybe pre-computation from a computer systems perspective to make this all efficient and fast. I think there'd be a lot of uses for this. Personalized Gemini, I'd love it if I could attend to all of my email state and photos and so on with my permission, of course. Web search, multimodal search and retrieval, like searching all the YouTube videos. Coding agents, like every coding agent at Google, it'd be nice if it attended to the whole Google code base for every Google developer. And then forward-looking, I think inference efficiency is going to be really critical, right? Like the training cost of these models is very large and you need a lot of chips. But going forward, more and more inference is going to happen, and more agents using these things in sophisticated ways and interacting with other agents that themselves are doing inference. So specialized hardware designed purely for inference is going to be important again, I think. Model and algorithmic improvements for efficient inference are going to be important. Low latency for these inference cases is a huge plus. It's just much more enjoyable to use something that responds in 100 milliseconds than 5 seconds. And I believe in the future that AI applied to automating chip design is going to be one of the ways in which we get much more efficient inference hardware. I have a whole talk on this, but essentially it's use learning as much as possible and RL. Okay, sorry, I'm running over. I have 2 more slides here. One of the other things that I did in the last couple of years is we got together a group of co-authors thinking about what are the impacts of AI in many different domains of the world, not just computer science. And we wanted to look at what these impacts might be, both positive and negative. And so we identified 7 domains we thought would be pretty dramatically impacted by AI. So employment, education, healthcare, misinformation, media, entertainment, governance and national security, and AI for science. And then we went out and we interviewed a bunch of domain experts in these areas. And in particular, tried to find people we thought would have interesting perspectives on one or more of these domain areas. And then we wrote up what we learned from chatting with the domain experts as well as our own thoughts. And so we produced a long archive paper, which not that many people have read. So we have a shorter version in CACM. And Dave Patterson, one of the co-authors, wrote a nice 1-page editorial in The Economist. And this is all available on shapingai.com. I think this is a pretty interesting paper. I think it has some good insights into what will the impact of AI be on, say, employment and technology transitions. as one example. It's the only paper I have with its own website. Okay, in conclusion, I think AI models like Gemini and products built with them these are becoming really important and powerful tools for the things we try to do every day. Further research and innovation is going to continue this trend. It's going to have a dramatic impact in many of the areas that I just mentioned in the Shaping AI paper. Healthcare, education, science, all kinds of things. It potentially makes really deep expertise. Like these models are really good in some areas, and it makes that available to many people all over the world, which is a pretty powerful capability. And done well, I think our AI-assisted future is going to be really bright. All right. Thank you.
We're running late. Just have a 5-minute question.
Okay.
No question? What's your biggest fear about AI?
My biggest fear of AI. I mean, I think there's a whole range of views on safety of AI systems and so on. I'm sort of the view that those are a little overblown. I think like careful engineering of what we allow AI systems to do will enable us to have like safe deployment of these systems, even though they are quite capable. I think misinformation is one that I'm worried about in the nearer term, because that seems like now we can create incredibly realistic video and audio things that are hard to distinguish even for super sophisticated people and with a lot of time to look at them. So that seems like one area that I think will be a worry. And I think also just how do we manage the impact of AI being able to do things that previously it wasn't able to do, and how do we make sure that people are prepared for those transitions and can learn to use these new tools and can be more productive and more effective using these tools than what could happen, which is all of a sudden people suddenly can't do that because it's been automated.
Question about like hallucinations and specifically like long-tail behavior, especially as we're getting more agentic workflows and like longer contexts. We know that like even so, past models have claimed to have 1 million context window at the limits of that 1 million context window, the retention and like the quality of responses degrades. Beyond simply adding search into the language model, what are other ways that like Gemini has been prioritizing decreasing hallucination, especially more like critical applications like role?
Yeah, I mean, I would say one of the key techniques is, instead of just generating a single answer, having multiple rollouts of potential answers, and then having the model itself look at those rollouts and assess which one it thinks is, or which pieces of them it thinks are most likely correct. That essentially is using much more inference time compute or chain of thought style thinking. Those kinds of things can be, definitely decrease the rate of hallucinations and make them. I mean, that's sort of the kind of approach we use in some of the IMO work, where you really can't afford to hallucinate anything because you need to prove this problem, that one of these 6 problems correct. And so that has been quite a good tool to rely on. But that also brings back the question of inference efficiency, because you really like for every answer to produce 16 answers and look at them and decide which ones or which ones you want to throw out and which ones you want to keep.
Yeah, I'm curious, what's your point of view of LLMs versus the emerging world models that are coming out now, or being worked on from a research perspective?
Yeah, I mean, I think world models are really just, do you understand, multiple modalities and how the world works from a physics perspective and so on. I think a lot of our Gemini models are actually pretty good at doing world models. If you look at the Genie 3 releases, those are built on top of Gemini models and enable you to generate sort of fairly sophisticated imaginary worlds with text prompts, and then control interaction in that world. So you can move left, move right, jump, move forward, and move back. And it maintains consistency with the world that it has created. And if you turn left and then turn back right, the things that were there are still there. So that's an important thing. We're actually collaborating with our Waymo colleagues because that enables them to create long-tail training cases in simulation. So you can say, please make a scenario where an elephant appears in the middle of the road. And that enables you to create, dozens and dozens of test cases that are really hard to actually have occur in the real world. And you can see how the car behaves, and it actually even synthesizes the LiDAR data that the system would have, enabling you to get better safety properties.
Maybe one more question. Jeff, you can pick.
So much pressure. All right. Not high, not low, but middle.
Hi. I guess like the last question is online research. I'm kind of curious, what type of research do you think we should work on without 1,000 GPUs? Because like a few of the directions you talked about, they're like pretty data intensive.
Yeah.
What do you think we can do to like help the AI forward?
Yeah, I mean, I think a lot of the kinds of work we do from a research perspective start as investigations at very small scale, right? And so I think where you can be quite effective is trying lots of different things that maybe you're not training on 1,000 accelerators, but you're demonstrating at small scale, this idea has legs, right? Like there's all kinds of problems in, say, continual learning or different model architectures, where I think at small scale, and in particular, one of the things we do is we run extremely, extremely small, and small. And we look at the trend of those things, because that trend is often more indicative of importance than exactly where it falls relative to the current baseline state of the art of our extra small or small model, right? If it's below the baseline, but the slope looks good, that's a really interesting idea. If it's above the baseline at the absolute smallest scale, but rapidly plummeting below the baseline, even at the small scale, that's less interesting. And so I think where people who don't have access to large scale compute can really do a great job is focusing on solutions that are quite different and quite interesting, and not stress about getting state-of-the-art results. And I think we as a community also should say, this is very different and unique and doesn't achieve state-of-the-art results, but it looks interesting at small scale. Like we should, as conference reviewers or whatever, celebrate that kind of thing than something that gets an incremental improvement on state-of-the-art by tweaking one little thing that is actually not that interesting.
Very good question.
Okay. Oh, thank you.